electric cars that dominated gasoline vehicles. By 1910, the situation in the American market was striking. Of all the automobiles traveling on U.S. roads, about 38% were electric, 40% ran on steam engines, and only 22% used gasoline. Yes, you read that right. Electric cars dominated gasoline cars at a ratio of almost 2-to-1. Just 3 years earlier, in 1907, a small company called Anderson Electric Car Company from Detroit introduced a production model that was named the Detroit Electric. An elegant city car with an enclosed body, a silent electric motor, and a range of up to 130 kilometers on a single charge. The speed reached 32 kilometers per hour, more than sufficient for the city streets of that time, where speed limits rarely exceeded 15 to 20 miles per hour. Infrastructure for electric vehicles was already forming. Charging stations appeared in New York, Chicago, and Detroit. And some enterprising owners were developing a concept that today is called battery swap. Discharged batteries were exchanged for charged ones in a few minutes, like modern gas refueling. Technically, electric cars surpassed their competitors in every parameter. Fewer moving parts meant fewer breakdowns and almost complete absence of maintenance. Starting with the turn of a key instead of the torturous cranking of a heavy starting handle, which could break your arm with engine kickback. This made the Detroit Electric especially popular among women. Among the owners were Thomas Edison, John D. Rockefeller Jr., and even Clara Ford, the wife of Henry Ford himself. The noise level was minimal. Gasoline automobiles roared and belched clouds of exhaust fumes. The electric car moved silently, not polluting the air, which was highly valued in cities just beginning to recover from the pollution of the Industrial Revolution. But in 1913, everything changed. Henry Ford launched the first moving assembly line for the Model T. Conveyor production crashed prices from $850 to $260 in just a few years. For the cost of one Detroit Electric, you could now buy 3 or even 4 Fords. The economic logic was ruthless. Almost simultaneously, the largest oil fields were discovered in Texas. Spindletop and other wells literally gushed oil. Gasoline transformed from expensive fuel into a mass commodity. The price per gallon dropped so much that a trip in a gasoline car became many times cheaper than an electric one. In 1912, engineer Charles Kettering invented the electric starter for gasoline engines. Now starting a car became as simple as an electric vehicle. The main competitive advantage of the Detroit Electric evaporated overnight. The oil industry aggressively developed infrastructure. Gas stations were built across the country, first along highways, then in cities and towns. By the mid-1920s, you could refuel everywhere. Electric stations couldn't compete. They required connection to electrical grids, which simply didn't exist in rural areas. The government began a large-scale highway construction program, stimulating interstate travel. Gasoline automobiles with greater range were ideal for this. The Detroit Electric, with its 130 kilometers, was perfect for the city, but useless for traveling between states. The last Detroit Electric rolled off the assembly line in 1939. Several specimens were preserved in museums, silent witnesses to an alternative path that humanity didn't take. The idea of rapid battery replacement was revived in the 2000s. The Israeli company Better Place tried to create a network of battery swap stations, but the project failed. Tesla also experimented with the technology, but focused on fast charging. History repeated itself. Economics once again defeated technical elegance. Today, electric vehicles face the same problems. Slow development of charging infrastructure, range anxiety, the colossal inertia of the existing network of gas stations. The only difference is that now, electric vehicles are backed by tech giants and government support in the fight against climate change. The history of the Detroit Electric reminds us, technology can be perfect, reliable, efficient, and still lose. Sometimes what wins is not the best solution, but the one that better fits into the economic reality of its time. Electric cars worked. They just didn't fit into a world that chose oil, assembly lines, and endless highways. The mechanical orchestra that played without musicians or electricity. In the 1890s, German immigrant Rudolf Wurlitzer founded a company in Cincinnati that began producing mechanical organs of unprecedented complexity. The device could reproduce the sound of an entire symphony orchestra without requiring a single musician or a drop of electricity. The machine performed any melody, from Bach to jazz, with accuracy indistinguishable from a live performance. The Wurlitzer organ operated on the principle of pneumatics and perforated paper rolls. Each perforation on the moving roll opened an air valve that directed airflow into a specific pipe, producing the right note at precisely the right moment. It was the same system as in music boxes, but refined to absolute perfection. The most famous model, the Wurlitzer Style 165, was a true engineering marvel. Inside the wooden cabinet, 174 pipes of varying diameter and length, drums, cymbals, bells, and wooden wind instruments. The system imitated the sounds of flutes, trumpets, clarinets, and xylophones, creating a full orchestral sound. The entire device was powered either by a hand crank or a simple mechanical drive. By the early 1920s, Wurlitzer mechanical organs were installed in thousands of locations throughout America and Europe. Silent film theaters used them for musical accompaniment to films. Restaurants and cafes created atmosphere with them. Amusement parks installed them on carousels and in pavilions. Large models, the Wurlitzer theater organ, were mounted in concert halls and replaced live orchestras. The library of perforated music rolls was constantly expanding. You could order popular tunes, classical works, marches, waltzes, and jazz compositions. Creating a new roll was labor-intensive. Music had to be transferred to the perforation system by hand. But once created, a single roll could be used thousands of times. Owners changed repertoires as easily as we change playlists today. The sound quality was astonishing. Contemporaries noted, in a blind listening test, it was impossible to distinguish a mechanical organ from a live orchestra if you couldn't see the sound source. Professional musicians acknowledged the accuracy of tempo reproduction, dynamics, and articulation. The organ lacked the improvisation and emotional nuances of live performance, but for background music in a restaurant or accompaniment to a silent film, it was more than sufficient. But in the 1930s, the world began to change. Electric phonographs appeared, more compact, cheaper to maintain, simpler to use. Radio spread rapidly, bringing music to every home for free. Sound film eliminated the need for live musical accompaniment. Now, music was recorded directly onto the film. The Great Depression dealt a blow to the entertainment industry. Many movie theaters, restaurants, and entertainment venues closed. Survivors looked for ways to cut costs. Mechanical organs were expensive and required constant maintenance. Pipes needed regular tuning. Pneumatic valves needed cleaning. Wooden parts needed protection from humidity and temperature fluctuations. Hiring a specialist became an unaffordable luxury when you could simply buy a phonograph and a stack of records. With the arrival of sound film in the late 1920s and early 1930s, the main niche for theater organs disappeared. Why have a huge, expensive mechanical orchestra when the soundtrack was already built into the film? Production of new Wurlitzer organs stopped. Thousands of existing instruments were dismantled, sold for scrap metal, or abandoned in basements and attics. Today, several hundred Wurlitzer mechanical organs survive in museums and private collections. Many still function, testament to the incredible reliability of mechanical engineering of that era. A community of enthusiasts restores old organs and creates new perforated rolls. At specialized festivals, you can hear how these instruments sound and understand why a century ago people considered them a technological marvel. A historical paradox. The perforated roll technology developed for musical automatons became a direct predecessor to computer programming. IBM punch cards, which were used to program the first computers in the 1950s to 60s, worked on the same principle. Information was encoded in a system of holes that the machine read and interpreted. The Wurlitzer organ was a programmable machine long before computers appeared. The mechanical organ didn't disappear because it stopped working. It disappeared because the world found a cheaper and more convenient way to reproduce music. This wasn't the victory of better technology over worse. It was the victory of economic efficiency over mechanical perfection. The elevators that never stopped. In 1884, British engineers patented a system called the Paternoster, named after Catholic rosary beads, whose links move in a closed loop. You walk into an office building, approach the elevator shaft, and see a chain of open cabins continuously moving up and down, like links in a giant escalator. You don't press a call button, you don't wait. You simply step forward at the right moment, jump into a passing cabin, ride to your floor, and just as easily step out while it's still moving. The concept was radically simple and brilliant. Instead of forcing an elevator to stop at each floor, accelerate, and brake again, the Paternoster moved continuously. A chain of 2, 3, or 4-person cabins rose up one side of the shaft, reached the top floor, flipped over the upper drum, and began descending on the other side. At the bottom, the process repeated. A closed loop, perpetual motion. No stops. Speed, about 30 centimeters per second. Slow enough to safely enter or exit, but fast enough for efficient movement. A passenger approached the shaft, waited for a cabin moving in the right direction to pass by, and at the moment when its floor was level with the floor of the landing, stepped inside. After a few seconds, the cabin reached the desired floor. The passenger exited with a quick step. No buttons, no doors, no waiting. The advantages of the system were measurable. Throughput exceeded ordinary elevators by 2 to 3 times. A regular elevator wasted time on stops, opening and closing doors, boarding and disembarking, acceleration and braking. The Paternoster simply moved. During rush hour, when hundreds of people simultaneously tried to go up into an office building, this difference became critical. There was no crowd in front of elevator doors. People entered and exited in a continuous flow. Energy efficiency was also impressive. The system never stopped, didn't waste energy on acceleration and braking, the most energy-intensive phases of regular elevator operation. The motor rotated at constant speed, consuming approximately 30% less electricity than an equivalent system of traditional elevators. Moreover, the weight of ascending cabins was partially offset by the weight of descending ones, which further reduced the load on the drive. By the mid-20th century, Paternosters had become a symbol of European architecture. In the 1970s, there were more than 60,000 of them across the continent. They stood in office buildings, universities, government institutions, research centers, and even some residential buildings. Germany, Czechoslovakia, and Great Britain were particularly committed to this technology. In Berlin, Prague, and London, entire districts of administrative buildings were equipped with Paternosters. Students at technical universities perceived them as an integral part of academic life, a quick way to move between lecture halls and laboratories. But continuous motion had a downside. The Paternoster required agility and attentiveness from the user. You had to correctly calculate the moment of entry and exit, not hesitate, not stumble. Most people mastered this skill after a few rides, but occasional building visitors sometimes panicked. Incidents occurred. Someone tried to jump out while moving and fell. Someone got stuck between the moving cabin and the stationary floor landing. Someone rode past their floor and in panic tried to turn around, which sometimes led to injuries. Statistically, Paternosters weren't more dangerous than regular elevators. Accidents were rare, and most resulted from gross violations of rules. But each such case received wide publicity. The press loved stories about killer elevators, although the real danger was minimal. Nevertheless, public opinion began to change. In the 1970s to 80s, new building codes and safety standards began to be introduced throughout Europe. Regulators demanded the installation of automatic doors, presence sensors, emergency braking systems, everything that made the Paternoster impossible by its very concept. Continuous motion and automatic doors are incompatible. Existing systems could be modernized, but it was so expensive that it was simpler to dismantle them and replace them with regular elevators. Insurance companies reacted predictably. They began raising insurance premiums for buildings with Paternosters and then refusing to insure them altogether. Building owners faced a choice: either pay huge sums for insurance and possible upgrades, or remove the Paternosters. Most chose the latter. Production of new systems ceased in 1974, when the last Paternoster was installed in an administrative building in Stuttgart. Since then, not a single new one has been built. Today, about 300 working Paternosters remain in Europe, mainly in old university buildings and government facilities that received special operating permits. The tallest system operates in Prague, 16 floors of continuous motion. These remaining Paternosters have become tourist attractions. People come specifically to experience the sensation of riding in a moving elevator. Periodically, ideas emerge about reviving the concept, with modern materials, sensors, and safety systems. But each such project runs into rigid certification requirements and astronomical costs of developing new standards. It's easier to build 10 regular elevators than to get permission for one Paternoster. The Paternoster didn't stop working. It didn't become technically obsolete. It simply didn't fit into a world that became obsessed with safety, standardization, and risk minimization. A world where a cabin moving without stops seems dangerous, even if statistics say otherwise. The technology was sacrificed to changing cultural notions of what is acceptable and what is not. Cars running on compressed air. In the 1890s, trams ran through the streets of Paris that produced no smoke, no noise, no emissions whatsoever. They ran on compressed air. The Mikarsky system used central compressor stations that supplied high-pressure air to all urban transport. Trams drove into special stations where tanks were filled in a few minutes and continued on their way. The technology worked flawlessly for decades. A century later, in 2000, the French company MDI decided to revive the concept. They unveiled the AirPod, a compact city car powered by compressed air. A 3-seat capsule with a futuristic design that looked like something from a science fiction film. The engine ran on tanks of compressed air at 300 bar pressure, 10 times higher than in car tires. The range reached 200 kilometers in city mode. Refueling took 3 minutes at a special station, or 4 hours from a home compressor plugged into a regular outlet. Maximum speed, 70 kilometers per hour, quite sufficient for the urban environment. The only exhaust was cold, clean air. Absolutely zero CO2 emissions. Operating costs were 5 times lower than a gasoline car. Because air is practically free, it seemed like the perfect solution for cities choking on smog. MDI attracted investors, began construction of a factory, signed preliminary agreements with distributors in several countries. The Indian company Tata Motors even announced plans for licensed production of the AirPod. The first production cars were supposed to appear in 2010. But the fundamental problem of pneumatic engines hadn't gone anywhere. Energy efficiency. When you compress air, about 90% of the energy expended turns into heat and dissipates into the atmosphere. Only 10% remains, which can then be used to power the car. This is a catastrophically low figure. Producing compressed air required electricity. The compressor ran on the electrical grid. And here, an inconvenient question arose. If you have electricity, why waste 90% of energy on compressing air when you can simply charge an electric car battery with about 90% efficiency? The Pneumobile turned out to be 10 times less efficient than an electric car using the same electrical energy. High-pressure tanks created another problem. 300 bar is enormous pressure. If such a tank ruptures, the result resembles the explosion of a small bomb. Special composite materials were required, multi-layered constructions, regular certification. Each tank needed to be inspected once every few years, an expensive procedure requiring specialized equipment. MDI tried to negotiate with various countries to create a network of refueling stations. But each country required its own safety certificates, its own standards, its own inspections. What was approved in France required complete recertification in Germany. What passed in Europe wasn't accepted in the United States. The bureaucratic labyrinth proved impassable. Production dragged on. 2010 passed. There were no production cars. 2012, still prototypes. 2015, MD. I announced the termination of development. The official wording: inability to achieve commercial viability. In practice, this meant the company had spent all its investment without managing to build a working business model. Tata Motors quietly shelved the project. Investors lost money. Several experimental AirPod prototypes ended up in private collections, expensive souvenirs of a failed idea. Pneumatic engines didn't disappear completely. They're still used in mines and chemical plants, places where any sparks or exhausts capable of causing an explosion or fire are strictly prohibited. Compressed air is absolutely safe in this regard. Some enthusiasts build pneumatic cars themselves for participation in eco-competitions, where what matters is not practicality, but demonstration of concept. Periodically, ideas for hybrid systems emerge: compressed air plus electricity. The concept is to use compressed air for short-term peak loads, sudden acceleration, climbing hills, and electricity for constant motion. Such a scheme could theoretically increase efficiency, but so far, not a single project has reached the production stage. The history of pneumatic cars is a story of an elegant idea colliding with brutal physics. A compressed air car works. It's clean, quiet, safe for the environment. But it consumes 10 times more primary energy than its electric competitor. And in a world where energy efficiency is becoming ever more important, this technology is doomed to remain niche, despite all its merits. Bioplastic from hemp, stronger than steel. In 1941, Henry Ford walked up to a prototype automobile with a sledgehammer in his hands. In front of journalists' cameras, he swung hard and struck the car's body. The panel slightly flexed and returned to its original position. No cracks, no dents. The metal body of a regular car would have turned into a pile of twisted iron. This body was made from hemp-based bioplastic. The hemp body car was the culmination of Ford's many years of experiments with alternative materials. The material was 10 times stronger than the steel of that time, and 3 times lighter. The production process required 70% less energy than metal smelting, and most importantly, the raw material was renewable. Ford planned to scale up production and completely transition to biomaterials by the 1950s. The technology was elegantly simple. Hemp fibers were mixed with plant-based resins under high pressure. The result was a composite material that could be molded into any parts: body panels, interior elements, load-bearing structures. The material was fully biodegradable. Unlike modern plastic, which takes centuries to decompose, the hemp composite disappeared in 6 to 12 months, leaving no toxic traces. Hemp as industrial raw material was ideal. It grew 4 times faster than forest. It didn't require pesticides. The plant itself suppressed weeds and repelled pests. It yielded enormous fiber output per hectare. The material cost was comparable to cheap metal, but its physical characteristics far exceeded it. But 4 years before the hemp body car presentation, in 1937, the Marijuana Tax Act was passed in the United States. Officially, a law on marijuana taxation. In practice, a ban on industrial cultivation of hemp of any variety. Industrial hemp strains don't contain psychoactive substances, but the law made no distinctions. To legally grow hemp, you had to obtain a special license, pay a prohibitive tax, and navigate a bureaucratic labyrinth that made the process economically senseless. Behind the law stood powerful lobbying. The oil and chemical industries actively promoted synthetic plastics based on petroleum. DuPont had just received patents for nylon and other synthetic materials in which the company had invested millions of dollars. Hemp bioplastic was a direct competitor, renewable, cheap, ecological. And this competitor needed to be eliminated. Newspaper magnates who owned timberlands were also interested. Hemp pulp could replace wood pulp in paper production, with much lower costs and many times faster. The coalition of corporate interests proved insurmountable. World War II redirected all resources to military needs. Metal was critically important for producing weapons, tanks, aircraft. The idea of replacing it with bioplastic seemed untimely. The government temporarily relaxed restrictions on hemp cultivation. The Hemp for Victory campaign was launched, calling on farmers to grow industrial hemp for army needs. But after the war, restrictions returned with doubled force. By the 1950s, petroleum-based synthetic plastics had completely captured the market. They were cheaper in mass production. The petrochemical industry operated at enormous scales and could undercut prices. Bioplastics couldn't compete when the very cultivation of raw materials was effectively prohibited or taxed prohibitively. The hemp body car remained a single prototype. The automobile survives today and is displayed at the Henry Ford Museum in Michigan, a monument to a technology that could have changed the world but was strangled in its cradle. Today, hemp plastic is produced in small volumes for premium ecological goods. Some automakers, BMW, Mercedes, use composite materials with hemp fibers for interior trim. This is niche application, a marketing move for environmentally conscious buyers. A full return to bioplastics is held back by the inertia of the petrochemical industry and lack of processing infrastructure. The history of hemp plastic is a story of technology destroyed, not by its shortcomings, but by political and corporate interests. The material worked. It was stronger, lighter, more ecological. But it threatened the profits of the largest corporations of its time. And that was enough to bury it. Steam locomotives. Without fire or fuel. In the 1880s, steam locomotives appeared in Europe that had no firebox, burned no coal, and produced no smoke. Fireless steam locomotives. The concept was simple and brilliant. Instead of carrying fuel and a boiler, the locomotive was charged with ready-made steam at a stationary station. The process took 10 to 15 minutes, and the accumulated steam was enough for 4 to 6 hours of work in switching mode, or for a run of up to 40 kilometers. The locomotive body was an enormous insulated reservoir, a thermos filled with steam at 10 to 15 atmospheres pressure and a temperature of about 180 degrees Celsius. As the steam was used to drive the pistons, the pressure gradually dropped, but thanks to effective thermal insulation, the process stretched over several hours. The technology was especially popular at industrial facilities, where boiler stations already existed. Chemical plants, oil refineries, gunpowder factories, anywhere there was a risk of explosion or fire, the use of ordinary steam locomotives with open flames was strictly prohibited. Fireless locomotives solved the problem perfectly. By the 1920s, Thousands of such locomotives were working around the world. They were indispensable in enclosed spaces and underground tunnels. The absence of smoke and ash made them the only acceptable solution for switching operations in workshops, warehouses, and mines. At gunpowder factories, where the slightest spark could cause catastrophe, fireless locomotives were the only permissible transport. Operating costs were 40% lower than ordinary steam locomotives. There was no need to purchase coal, hire stokers, clean fireboxes and chimneys. The locomotive pulled up to the steam station, connected to the main line, refueled, and left to work. Maintenance was reduced to periodic inspection of the reservoir and steam mechanisms. But starting in the 1950s, mass dieselization of railways began. Diesel locomotives didn't require steam station infrastructure. They were autonomous, could work anywhere. Refueling took minutes. For industrial enterprises, this meant freedom. No need to build a boiler house, maintain steam facilities, keep a staff of stokers for stationary boilers. Electrification of industrial sections made electric locomotives even more advantageous for switching operations. Electricity was available everywhere industry was. An electric locomotive didn't need refueling. It simply worked as long as it was connected to the overhead wire. No boiler maintenance, no steam systems. Stationary boiler stations were gradually decommissioned. Steam heating was replaced by electric and gas. Steam infrastructure became obsolete. When the boiler houses disappeared, so did the infrastructure for fireless locomotives. Locomotives without fireboxes became useless without a source of steam. The technology was fundamentally dependent on proximity to a steam station. It was never suitable for mainline transportation. Too limited range, too frequent refueling. Fireless locomotives were created for switching work in a limited area, and when that niche disappeared, so did they. Today, several dozen fireless locomotives are still operated at industrial facilities in Germany and Japan, where steam systems have been preserved for historical reasons, or where safety requirements don't permit the use of diesel engines. Museums of steam technology in Europe maintain historical specimens in working condition, living monuments to an era when steam was the king of industry. Curiously, the concept of stored energy has been revived in modern heat storage systems for renewable sources. Solar and wind power plants use excess energy to heat enormous reservoirs of molten salt or water, which then gradually releases heat for electricity generation. The principle is the same as in fireless locomotives. Store energy when it's available, use it when it's needed. Fireless locomotives didn't stop working. They simply lost their habitat, a world where steam boiler houses were everywhere. The technology was perfectly adapted to its time and disappeared along with it. Video calling that worked in the 1920s. On April 7, 1927, a crowd of journalists gathered in the AT&T office in New York. Before them stood a screen about the size of a modern iPad. On the screen appeared the face of a man located in Washington, 360 kilometers away. The man spoke. His lips moved in sync with the sound. He smiled, nodded. This was the first public demonstration of two-way video calling. The technology we today call video calling worked in 1927. Herbert Ives, an engineer at Bell Laboratories, spent years developing a system for transmitting moving images over telephone wires. The quality was modest, 50 scanning lines, which roughly corresponds to a resolution of 50 by 50 pixels in modern terms. But it was enough for recognizing faces, gestures, and basic facial expressions. The experiment participants conducted a full conversation, seeing each other in real time. The camera used mechanical scanning, a NIP-cow disc with holes arranged in a spiral. The disc rotated in front of the lens, sequentially scanning the image line by line. Photoelectric cells converted light into an electrical signal, which was transmitted over standard telephone lines. On the receiving end, the process went in reverse. The electrical signal controlled the brightness of a lamp that shone through a synchronously rotating nip-cow disc, recreating the image. Transmission speed, 18 frames per second. This is the minimum for perceiving motion as continuous, though with noticeable flickering. Contemporary cinema used 24 frames per second, so the quality was comparable to the cinematography of that time. The system worked over ordinary telephone lines, requiring no special infrastructure. AT&T planned to launch a commercial videophone service by 1930. The press enthusiastically wrote about the television telephone of the future. Futurists predicted that in 10 years, every home would be equipped with a videophone. AT&T engineers began designing compact home devices. It seemed the era of video communication was about to arrive. But economic reality proved harsh. The cost of one video call between New York and Washington was about $16, which, adjusted for inflation to modern money, exceeds $100 for a few minutes of conversation. The equipment was bulky and expensive. For the mass market, this was completely unrealistic. In 1929, the Great Depression began. Funding for technology projects collapsed. AT&T froze developments in videophony. The company's very survival was in question. People were losing jobs, banks were closing. The idea of $100 video calls seemed absurd in a world where millions couldn't afford regular food. Telephone networks weren't ready for mass video transmission. Each video call required bandwidth equivalent to several dozen regular voice calls. To make videophony accessible, the entire telephone infrastructure of the country needed modernization, investing millions in new cables, amplifiers, switches. In Depression conditions, this was impossible. Radio and cinema diverted public attention. Radio brought music, news, and entertainment to every home for free after purchasing a receiver. Cinema offered sound and high-quality moving images for pennies. Video communication seemed an expensive luxury against the backdrop of affordable entertainment. Why pay $100 to see the face of your conversation partner when you can call for a couple of cents and hear their voice? World War II redirected engineering resources to military communications. Radar, encryption, radio communication for troops. These were the priorities. Videophony moved to the back burner and stayed there. The video communication concept fell asleep for 40 years. In 1964, AT&T introduced the picture phone, the first commercial video phone. It was smaller, image quality was higher, but the cost was still prohibitive. The service launched in several cities. The failure was complete. Over years of operation, they managed to sell only a few hundred devices. People simply didn't see the point of paying huge sums for a feature they had done perfectly fine without for decades. Only with the advent of the internet in the 1990s did video communication become accessible. First, in terrible quality, with freezing and delays. Then, better and better. And finally, in the 2000s, with the emergence of Skype, FaceTime, Zoom, video calls became so commonplace that we don't even think about using them. The technology was ahead of its time by 70 years. It worked in 1927, the same way it works today. But the world of 1927 wasn't ready economically, infrastructurally, or culturally. People didn't need video communication. They needed affordable voice communication. And when the technology finally became accessible and free thanks to the internet, it turned out they really did need it. It just took almost a century. The solar power plant, built in 1913. In 1913, a power plant operated in the Egyptian desert near Cairo that didn't burn a gram of fuel. Rows of parabolic mirrors, 62 meters long, reflected sunlight onto water-filled tubes, heating it to 200 degrees Celsius. Steam turned turbines, producing 55 horsepower, enough to pump 26,000 liters of water per minute, providing irrigation for thousands of hectares of cotton fields. The plant worked stably, free of charge, and safely for the environment. American engineer Frank Schumann spent a decade developing solar thermal energy technology. His calculations showed, if solar concentrators covered just 1% of the Sahara's area, it could provide energy for all of humanity. No fossil fuels needed, no mines needed, no transportation of coal and oil across oceans. Energy simply falls from the sky. Take it and use it. The technology was elegantly simple. Parabolic mirrors focused sunlight on black tubes through which water flowed. The water heated to boiling temperature, turning into steam. Pressurized steam was fed to standard steam turbines, the same ones used in coal and oil power plants. No exotic materials, no complex chemical processes. Mirrors, pipes, water, turbines. The system's efficiency reached 11 to 13%. That is, of all the solar energy falling on the mirrors, 11 to 13% was converted into electricity. This is comparable to early 21st century photovoltaic panels that appeared nearly a century later. For 1913 technology, this was an outstanding result. The cost of energy was lower than coal plants in regions with high solar activity. Egypt, the Arabian Peninsula, North Africa, the southern United States. Anywhere the sun shines 300 days a year. Schumann's solar plants were more economically viable than traditional energy. Initial investments paid off within a few years, after which energy became practically free. The sun doesn't send bills. Schumann attracted investors from Britain and Germany. Large solar power plant construction was planned throughout the Middle East and North Africa. New, more efficient concentrators were being designed. Heat storage systems for nighttime operation were being developed. The future looked sunny in a literal sense. And then World War I began. August 1914. Europe plunged into chaos. Investors urgently left Egypt. Funding ceased instantly. British and German companies that had invested money in the project were now on opposite sides of the front. No one thought about solar power plants anymore. There was a war for the survival of empires. Almost simultaneously, large oil deposits began to be discovered in the Middle East. The Persian Gulf, Iraq, Saudi Arabia. Oil literally gushed from beneath the ground. It was cheap, transportable, energy-dense. Oil's strategic importance became obvious during the war. Armies, navies, aviation ran on liquid fuel. Solar energy seemed like a frivolous toy in a world where oil decided the outcome of battles. Engineering resources were reoriented toward military needs. The best minds worked on tanks, aircraft, submarines, chemical weapons. Solar technology development stopped. No one invested in peaceful energy in the midst of global carnage. After the war, the coal and oil industries completely dominated energy. Huge corporations with billions in capital controlled the extraction, processing, and distribution of fossil fuels. They built power plants, oil refineries, pipelines. Investments went into traditional technologies that brought guaranteed profits. Solar energy seemed like an exotic curiosity, with no commercial future. Schumann's plant in Egypt was abandoned. Mirrors were looted by locals. Metal went for household needs. Pipes rusted. Turbines stopped forever. By the 1920s, not a trace remained of the first working solar power plant. The desert sand swallowed the ruins as if they had never existed. The technology was forgotten for half a century. Only in the 1970s, during the oil crisis, when oil prices quadrupled, did humanity remember solar energy. But everything had to be invented anew. Schumann's blueprints were lost. No one remembered the technical details. The concept of solar thermal plants was revived in the 1980s. Today, the largest CSP stations, concentrated solar power, operate in Spain, the United States, Morocco, and China. They used the same principles as Schumann's 1913 plant: mirrors, water, steam, turbines, just with improved materials, computer control, energy storage systems. If the technology hadn't been abandoned in 1914, if investments had continued, if not for the war and the oil boom, humanity could have arrived at renewable energy 70 years earlier. We could have avoided a significant portion of climate change associated with burning fossil fuels. But history knows no subjunctive mood. Schumann's plant worked. The technology was real, economically viable, scalable. It didn't lose to a competitor with better characteristics. It lost to war, oil, and historical bad luck. Mechanical watches with lifetime guarantees. In the early 20th century, when you bought Swiss mechanical watches, you weren't just acquiring a device for measuring time. You were getting an instrument designed for a century of continuous operation, with a lifetime guarantee and the right to pass it down as an inheritance. Patek Philippe, Vacheron Constantin, Audemars Piguet. These companies created mechanisms that your grandchildren could wear with the same confidence as you. Mechanisms were calculated for 100 or more years of operation with minimal maintenance. Oil change once every 5 to 7 years. That's all that was required. The manufacturing quality was so high that century-old watches still work today with accuracy to within a few seconds per day. Many of them are more accurate than modern mid-range mechanical watches. Every part was manufactured with a safety margin of 3 to 5 times. Gears, axles, springs, everything was made to withstand loads many times greater than operational ones. Mechanism wear stretched over decades. Craftsmen knew these watches must outlive not only their owner, but his children as well. Companies maintained archives of blueprints and production of spare parts for all models ever released. Patek Philippe can still repair any of its watches, even if they were produced in 1839, the year the company was founded. This isn't marketing. This is real policy followed for nearly 2 centuries. The philosophy was simple and logical. The customer buys a watch once in a lifetime. The company profits from service, repair, and reputation. A satisfied owner recommends the brand to friends, passes the watch to children, who also become customers of service centers. The business model worked stably from the 1850s through the 1970s. More than 100 years of steady, predictable growth. And then the quartz revolution began. In the 1970s, Japanese companies Seiko and Casio launched mass production of quartz watches. The cost dropped 50-fold. Quartz mechanisms were more accurate. The margin of error was measured in seconds per month, not per day. They were cheaper. Plastic case, electronic board, battery. They required no maintenance. Wear them until the battery dies. Replace it, and wear them on. But they couldn't be repaired. When the mechanism failed, the watch was simply thrown away. Planned obsolescence became the new norm. Why make eternal watches when you can sell new ones every few years? The Swiss watch industry experienced a crisis called the Quartz crisis. Dozens of companies went bankrupt. Employment in the industry fell from 90,000 people to 28,000 in a decade. Entire towns that had lived by watchmaking for centuries became deserted. Surviving manufacturers were forced to adapt. Mechanical watches stopped being positioned as precision instruments. Quartz was more accurate. They became luxury items, status accessories, works of art. The philosophy changed. Watches were no longer made to last centuries. Even expensive mechanical models were often designed so that, after 20 to 30 years, repair would become impossible or unprofitable. Today, only small manufactories like A. Lange and Söhne and Patek Philippe still follow the old principles. But prices start at tens of thousands of dollars. This is no longer a tool for everyone. It's an object for collectors and very wealthy people. The vintage watch market is thriving. Century-old mechanisms are valued higher than new models precisely for their manufacturing quality. Collectors know watches from the 1920s or 1950s are made with a safety margin that modern manufacturers don't even think about. The paradox: to buy truly reliable watches, you need to buy old ones. The concept of eternal design has almost completely disappeared from the mass market. Replacement has displaced repair. We live in a world of disposable things, even when it comes to mechanisms that are technically capable of working for centuries. Mechanical watches for life didn't cease to exist because they became technically impossible. They disappeared because the economic model changed. In a world where profit depends on constant sales, eternal things are a threat to business. Trolleybus networks, 10 times cheaper than subways. By the 1950s, hundreds of cities around the world had built trolleybus networks as the foundation of public transportation. Moscow by 1960 had the most extensive system in the world, more than 600 kilometers of lines. Los Angeles, San Francisco, London, Berlin. Trolleybuses ran through the streets of the planet's largest cities. The system was 10 times cheaper than a subway, deployed in months instead of years, and required no tunnel digging. Trolleybuses were silent, produced no exhaust, and worked in any weather. Electric motors provided smooth acceleration and high energy efficiency. Efficiency reached 80%, which was many times better than diesel buses. The absence of rails allowed maneuvering and bypassing obstacles. Unlike trams, a trolleybus could deviate several meters from the main line, drive around a parked car or roadwork site. The cost per kilometer of trolleybus line was 20 times lower than a kilometer of subway. Building a line required installing poles along the road and stringing overhead wires. Construction time: months. A subway required digging tunnels, building stations, complex engineering systems for ventilation and safety. Construction time: years, sometimes decades. But in the 1960s to 70s, mass motorization began. Cities were designed for personal transportation, wide avenues, multi-level interchanges, parking lots. Public transportation was perceived as a relic of the past. The future was seen in personal automobiles for every family. Oil companies actively lobbied for the transition to buses with diesel engines. Trolleybuses ran on electricity. The oil industry got nothing from this. A diesel bus consumed fuel that had to be constantly purchased. The economic interest was obvious. Municipalities were offered favorable terms for purchasing diesel buses: loans, subsidies, technical consultations. Overhead wires came to be considered aesthetically unappealing. In the era of modernism, when architects dreamed of cities of the future with glass skyscrapers and clean lines, wires above the streets were perceived as visual clutter. Cities wanted clean skies. Wires were associated with outdated technology, although functionally they worked flawlessly. Subway construction received more government investment. A subway is a prestigious project that allows politicians to cut ribbons at station openings, demonstrate technological superiority, leave monuments to their rule. Trolleybus lines don't provide such photogenic moments. They just quietly work. By the 1990s, many cities dismantled their trolleybus networks. Wires were cut, poles removed, trolleybuses sent to scrap metal. They were replaced by diesel buses, more flexible in routing, not dependent on infrastructure, and significantly dirtier. Exhaust, noise, diesel smell. All of this returned to streets that had breathed clean air for decades. But starting in the 2000s, the situation began to change. Cities are suffocating from exhaust fumes. The climate crisis demands transportation decarbonization, and suddenly it turns out trolleybuses are exactly what's needed. Zero emissions, high efficiency, proven technology. Modern systems use autonomous batteries for movement on sections without wires. Hybrid trolleybuses. They can turn off the main route, bypass traffic jams, reach the depot without the overhead wire. The best of both worlds, trolleybus efficiency and bus flexibility. Several European cities are restoring dismantled lines. Zurich has preserved its system and is expanding it. Salzburg is discussing the return of trolleybuses. Paris is considering projects for new lines. Technology that was abandoned 50 years ago is relevant again in the era of decarbonization. Trolleybuses didn't become obsolete. They simply didn't fit into a world obsessed with cars and oil. Now, as that world begins to change, it turns out the old solution works better than many new ones.